In this video, we will discuss duration and convexity using a problem similar to one out of the excellent text Options, Futures, and Derivatives by John Hall. Portfolio A consists of a one-year discount bond with a face value of $1,000 and a 9-year discount bond with a face value of $5,000. Portfolio B consists of a 6.5-year discount bond with a face value of $5,700. The current yield on both bonds is 10% per annum using continuous compounding. Question A, show that both portfolios have the same duration. Question B, show that the percentage changes in the values of the two portfolios for a 0.1% per annum increase in yields are the same. Question C, what are the percentage changes in the values of the two portfolios for a 10% per annum increase in yields? And question D, which portfolio has the highest convexity? So we will start with question A. To calculate the duration, first we have to calculate the portfolio value. So the value of a bond portfolio is the discounted sum of all cash flows, which looks like this if you use continuous compounding. For portfolio A, we have a $1,000 cash flow occurring in year one, and our initial interest rates are 10%. So portfolio A equals 1,000 exponent minus 0.1 times 1 plus the next cash flow of 5,000 occurring in year 9, also discounted at 10%. And we do the calculation in Excel. 1,000 exponent of minus 0.1 times 1 plus 5,000 exponent of minus 0.1 times 9 gives us $2,937.69. So that was from the equation right here for the bond or portfolio's price. Now we need to use the next equation here for the duration of a bond or portfolio. Duration equals, again, the discounted sum of all the portfolio's cash flows, but now multiplied by the time in which each cash flow takes place, all of that summed and divided by the bond's price. So for the duration of portfolio A, we have the first payment occurring in year one times the dollar amount of that payment of 1,000, present value thereof, plus the second payment occurring in year 9, and then the present value of that divided by the bond's price, and that gives us the duration here. So we get 1 times 1,000 exponent of minus 0.1 times 1 plus 9 times 5,000 exponent of minus 0.1 times 9 divided by the bond's price of I-15 of 2,937.69. And therefore, we get the duration of the bond of 6.5359 years. The duration of the bond is an estimate on average of how quickly you get your money back. So for this bond, it would have to be somewhere between year 1 and year 9. For our second bond, our portfolio B, it is a zero coupon bond, so we get all of our money back in 6.5 years. Therefore, the duration will be the same as the maturity, 6.5 years. And we will show that exactly. So first, the bond's price is going to equal the 5,700 exponent of minus 0.1 times 6.5. 5,700 times exponent of minus 0.1 times 6.5 gives us an initial price of 2,975.66. And then the duration, we will take the 6.5 years times the 5,700 exponent of minus 0.1 times 6.5 divided by the bond's price of 2,975.66, and then that gets us here a duration of 6.5 years. So the problem is designed so both of the initial prices are similar and both of the initial durations for the two portfolios are similar. We have now shown that both portfolios have very close to the same duration. For part B, show that the percentage changes in the values of the two portfolios for a 0.1% per annum increase in yields are the same. Well, one of the purposes of duration is to match the duration of assets and liabilities for a bond portfolio, or for example, for a bank. And that is why this equation was developed in the first place. These are the first two terms in a Taylor series analysis. So the change in a bond's price is going to be minus the bond's price times the duration, assuming continuous compounding, times the change in interest rates, plus 1/2 the convexity times the change in interest rates squared. And if we did the full Taylor series analysis, you would have a cubic term, a term of change in interest rates to the fourth, etc. So why we did this is so you could match the duration of the assets and liabilities, and therefore immunize a portfolio against change in interest rates to prevent things like the savings and loan fiasco that is discussed in another video. So in this example, we have made the two durations the same. So for small changes in interest rates, the change in the portfolio's price should be the same. And you can see that on the graph right here, which we also develop in another video. So here we have a graph of bond prices versus interest rates. The blue line is bond A, the orange line is bond B, and the gray line is the duration approximation. So in reality, bond prices change in a curved manner, a convex manner, but for small changes, you can approximate that as being linear, right in here. And a 0.1% increase is a small change, so we're merely going from here to here. If interest rates go up, the bond prices should go down, and since these two portfolios of bonds have the same duration, they should go down by about the same amount. And we will show that here. So this is our initial price of portfolio or bond A. We will recalculate it for the new interest rate, which went from 0.1 to 0.11. So the new price of our portfolio is 1,000 exponent of minus G13, 0.11 times 1, plus 5,000 times exponent of G13, which is 0.11 times 9. And that gives us a new bond price of 2,753.72. So interest rates have gone up. So our bond price has gone down from 2,937.69 to 2,753.72. The percent change of that is the final bond price here minus the initial bond price here divided by the initial price for a decrease in value of around 6.3%. We can do the same calculation here for bond B. Well, for bond B, we have a zero coupon bond, a payment of $5,700 times exponent of minus, now again, G13 of 0.11 times 6.5. And we find our bond price for B has decreased from 2,975.66 to 2,788.40. And again, to figure out the percentage change, we take our final bond price minus our initial bond price divided by our initial bond price, and we get a decrease in the bond price of around 6.3%. So for this small increase in interest rates, our linear duration approximation works, and the two bond prices have decreased by the same percentage for a change from 0.1 to 0.11%. Now we look at question C. What are the percentage changes in the values of the two portfolios for a 10% per annum increase in yields? Our initial interest rate demanded by the market was 10%. Now we're going to say it's going up to 20%. As interest rates go up, bond prices go down, and we can see here that this is a big enough increase in interest rates that our linear duration approximation does not work very well anymore. So the duration approximation overestimates the decrease in the bond's price. Right here would be the duration approximation. Again, our orange line is bond B, our blue line is bond A. And we can do that exactly down here. So let's calculate the new value of portfolio A. We will have 1,000 exponent of minus J13, which is now 20% times 1, plus 5,000 exponent of minus J13 of 20% times 9. So the new value of portfolio A is 1,645.23. The initial value was 2,937.69. So if we want to get the percent change, we take the final value here, D25 of 1,645.23, minus the initial value of I15 of 2,937.69, divided by the initial value, and we get a percentage decrease of minus 44%, a pretty significant loss in value. We will do the same calculation over here for the second bond, bond B. Bond B, again, has a face value of 5,700. It's a zero coupon bond maturing in 6.5 years, and we are now discounting it at 20%, and we get the new price of bond B of 1,553.43. So if we want the decrease in the value of portfolio B, we will take I-25, our final value here, 1,553.43, minus our initial value of I-18, which is here, of 2,975.66, divided by our initial value of I-18, and we get a 48% decrease in value. So we can see as interest rates go up, bond prices go down, and the value of bond B has gone down more than A. As you can see right here in red, B is below A. So the final question is, which portfolio has the highest convexity? Well, duration being negative is linear here, but the second term convexity is positive, so duration always underestimates the price of a bond, whether it's from interest rates going up or interest rates going down, and the bond with the highest convexity will be the one for which the price of the bond is underestimated the most. So in this case, the blue line is above the orange line, and the decrease here for bond or portfolio A is less than bond or portfolio B. So portfolio A, the blue line here, has the larger convexity since it has the lower percentage change. I thank you for watching this video.